Okay, thank you a lot for your presentation. Good afternoon, everyone. So, the title of my presentation is Round Robin, a Global Virtual Lab for Measurement, Data Analysis, and Presentation of Results. So, I will start discussing why do we need round robin. Then I will do a quick review from the past with some round robins and inter-laboratory study that has been done with the main purposes of finding a protocol for measurement in order to have more adherence coherence between different laboratories. Then what has been done new since then. Then I will move to the topic of large data handling that is becoming more and more important. And finally, I will introduce the new round robin. So why do we need round robins? We need round robins because we want to be able to compare results. And to do that, it's important that we set some standards and also that we test the standards to make sure that they actually work. And also, more important, also we want to share the experience that we have acquired and also join efforts into the OPV field. So one of the first inter-laboratory study that was done was published in 2009. And this was done in 18 different labs on the western part of the world. Denmark provided, DTU provided some solar cells. And this first inter-laboratory study proved that it was possible to do such kind of study with OPV as well. The graph shows some data where we have initial performance measured DTU versus the recipient measurement and the final measurement result when the sample came back. However, we see a large variation, so we need to improve this. So what was done in 2011 was another inter-laboratory studies, this time with 24 different labs in 4 different continents. And here there was developed a protocol for carefully measure the solar cell performance. As you can see, the cell was masked, and it was placed under a simulator for 5 minutes before measuring in order to make sure that the temperature was stable. And this way, for example, DTU was able to reduce the standard deviation of above 50%. The second part of this inter-laboratory studies dealt with stability analysis. And when we look at this graph, we see that when we change the type of lamp indoor, we have very different degradation. For example, I can just point that metal halide and xenon arc lamp are the one that gives the best match with the outdoor lifetime. While in the right plot, we see different degradation rate depending on the relative humidity concentration. So this made clear, once again, how we needed to develop some protocols to compare lifetime studies. In 2014, there was a test of this standard. And you can see with the blue points, damp heat test. With the green one, it's a shelf life test. And the brown points are high temperature in the oven test. And you can see how we have a really good match and adhesion among the different laboratories. However, it is important to say here that the tests are needed, protocols are needed, but also the device have to be reproducible, and especially the encapsulation have to be the same, otherwise this will not be possible. So this is an important topic. So another point was to prove not only in inter-laboratory study, but also round robin. So in this case, the difference is that the same set of samples are sent among different labs. And with this specific one, there was also included a silicon device that was used to make sure that the deviation was caused by actually OPV and not by equipment error. And you can see that the OPV has caused a deviation on the short circuit current that is comparable with the silicon one, except a few labs. So this proved this concept also for OPV. When we look at this graph instead, we have different solar cells. So A1, A2, B1, B2, and C1, C2 are different devices. And each column represents the deviation from average of the short circuit current for each different labs. The red columns are indicated whether a lab were not completely following the measurement protocol. And you can see that if you're not careful enough, you can actually achieve a very high deviation from average. So this again proved that we really needed to make sure that we follow protocols. So the next step was to make sure that this variation was not because of the user of the operator that was actually making the measurement, but it was something intrinsic of the equipment of the protocols. So this round robin 2013 was done by the same operator that traveled among 21 different labs in China. And you can see that the deviation was still very high. So this proved that it's more important to have the right equipment and to follow the protocol. And another found in this study was that actually short circuit current was the parameter that was affecting, for the most part, the power conversion efficiency variation. So when we are sure that the operator is not playing a major role, so we want to make sure that we use the same equipment and see if we can actually reduce again the variation. And with the Suitcase round robin, we do that. So there were 4 different Suitcases traveling around different countries and continents. And people could measure the solar cell with the same equipment and with a very specific protocol and with the outdoor real sun. So we try to minimize as much as possible interference by labs equipment. And this worked, and we were able to reduce the variation once again. We also developed an internet portal for both tracking the Suitcase and also to allow people to easily report the data. I want also to point out here that there were different devices inside with different design, and each of them led to different variation finally. So what we are doing now is work with different type of device, different technologies, and benchmark the lifetime, and because we want to find the best candidate for round robin studies. So we have spin coated with this unencapsulated one and the encapsulated one. Then we have the mini roll coated device, which can be again unencapsulated or encapsulated and fully encapsulated with the fully sealed of the edges as well. And then we have the bigger one, 3OPV, that are done with the roll-to-roll machinery. So we want to make sure that we have reproducible device. And this, it's both considering the initial performance that are shown in this graph. As you can see, 3OPV is the one that gives the less variation, standard variation. Then we have, which is in blue, and in gray we have the mini roll coating, which are the second in order of variation. And then we have the spin coated one in white, which shows the most spread in this type of plot. And the second part that we want to make sure it's reproducible is the stability. So we have developed a graph that we use for comparison of lifetime. We call it O diagram or OPV diagram. I will talk about this in detail. For now, it's a graph that allows to have a comparison of different technologies, OPV technologies. It gives information both regarding the burden-in phase and the stabilized phase. You can also see the encapsulation effect, and you can distinguish between harsh and moderate tests, ISOs tests. This was also done using the software approach, so the data points are generated in a semi-automatic way. So we have in the x-axis time scale, which is given in days, and I'm using a logarithmic scale in 4 base, which have to relate these values with time units such as hours, days, weeks, months, season, and years. And in the y-axis, we have initial performance and stabilized performance. So when we take a point which is filled, I'm sorry, this is very small. I don't know if all of you can see it. But when we see one point which is filled, this is giving the initial performance, so E0, in function of T80 in the scale. So we have an information about the initial part and the burden-in phase. So when instead we look at the empty point, this is plotting the stabilized phase, so ES, and in function of TS80. And this is so giving information about the stabilized part of the degradation curve and how stable or unstable it is. Then we have 2 colors in the plot. We have a red color, which is giving data for unencapsulated device, and a blue color for encapsulated device. So when we look at, for example, ISOs D3, L2, L3, we see that the unencapsulated ones fall in a region that I call unstable, which is less basically than hours. And therefore, we consider this test as harsh test. They kill your device very fast. While if you look at those at D1 and D2 ISO tests, they are more stable and they go from hours to even weeks. Also, when we move from the red points, so unencapsulated, to encapsulated ones, so blue points, we can see that we can identify some kind of ratio or distance in the stability. And this is on average about 4 orders of magnitude in this scale for the harsh test, while it is approximately 2 to 3 for the moderate test. And it is possible with this kind of plots not only to relate this indoor test, but also to have a look at the outdoor data. So I encourage you to use the same kind of plot, because we want to have more and more data points in this type of graph, because finally we would like to use this as a tool for lifetime prediction. And we are still in an early stage. However, the idea is that you will perform a fast and harsh test, and that looking at the ratio among the different tests, you can try to predict the lifetime with a certain uncertainty, of course. So if we then look at the same type of device, same architecture, and we vary the encapsulation, we have such kind of plot. And this plot has in the vertex different encapsulation. So we have mineral coated with different encapsulation, partial and full, free OPV, and the spin coated glass full. And this is normalized to this lifetime because it's the more stable one. So what anyway it's clear from this graph is that free OPV and spin coated glass full are very good, are very stable, and this make them as very good candidate for round robin study, while the mineral coated device are not that good, so they're not still very compatible with the round robin concept. So when we have all these data points and all this number of variation of parameters, we end up with a lot of data, and therefore we use a database to organize our data, to collect it. Particularly, we use MySQL, which is the world's most popular open source database. It includes a search tool. You can organize it as you want, and it's very customizable. You can easily share stability data. And you can include plotting tool and web application that talk directly to the database. So we use MySQL, for example, for tracking the, this is supposed to start, sorry. To track the number of free OPV that we ship. Okay, I have a problem. It says the QuickTime is not available, and this is supposed to run. Okay, I will go on just a second. Okay, never mind. Okay, so this was supposed to be a video where I was in this world map. If in the meantime you can open your PC and try to see if it works in yours, then I connect yours. Because I have also another video that I really want to show you. This is not critical, but the next one it is. So this was supposed to show a lot of points that will show up in the map, and they automatically give an idea where our free OPV samples are sent. And they are above 7,000 samples at the moment, so it's really important how we really need this kind of approach. So this part of the talk, we have learned that we need more control in order to achieve better reproducibility. And especially, we need reproducibility in terms of device performance that, for example, we can achieve with free OPV. We need to have the same measurement equipment, or we need to control it in order to make sure that we have good reproducibility again, measurement protocol, and environment. And it's difficult to control all these factors among different groups, of course. However, today, I think we move one step closer to this reproducibility, and I would like to introduce a new round robin. And especially I would like to introduce the MMkit, which stands for Multi-Measurement Kit. And it is a tool that is based on Arduino, which is an open platform for electronic. It is connected to some number of sensors, so it can measure IV curves. It has temperature sensor, it has humidity sensor, and an irradiance sensor. All this measurement tool acquire data which is stored in an SD card, so you can easily move the data to your PC. You can also see the data, what you're measuring in a screen. And also, you can transfer the data with an Ethernet cable to the internet into an external database. The internet connection allows also to browse directly the Arduino and also access the data that are stored in the SD card without turning off the device. This is how the system looks like. I also have it here. It's very compact. So this is it. It's very compact. So you have this is the main hardware, which controls basically the system. And then we have the sensor board that you can place inside your aging chambers, and you can connect to it the device, so you are able to track all the parameters of your environmental chamber and also measure the solar cell. Just some advantage of it. So it's very low cost, but nevertheless it's quite accurate. For example, I can talk about the source meter as a resolution of 1 microampere. If you take, for example, the Kitli, which we are using, that has a resolution of about 100 nanoampere. But if you look in the website, it costs $4,000. So I'm not saying that you have to replace your equipment with this, not at all. But I'm just saying this is a low-cost tool which is compatible with round robins because it's very compact. We can ship it around, and it's still, nevertheless, quite powerful and quite accurate. So I would like to show you a demo if the video works. And yeah. And for the demo, I'm using some open source software. So I'm using the tool, and I'm using R, which is a statistical software, MySQL and Google Chart for plotting the graphs. Yes, it works. Okay, cool. So this is our simulator. We place in the cell. And now the Arduino will start to measure. So this is the part of the Arduino. This is measuring temperature, irradiance, and the IV curves. And this is automatically exported to the database that you see in the background, which is very organized. And this is the function that allows to directly look into the SD card. So you type in the IP address of the tool, which is shown anyway on the screen. So it's very easy to find. And once you go inside, you can see what are the files stored in the SD card. You can click on them, and you can easily see the data that is stored. For example, I click in the IV curve, and you can see that this is loaded quite fast. You can copy, you can store it, you can see what the tool is measuring. And also, using R and using Google API, you can generate this kind of overview in a very automatic way, so it's one click. On the left, you have IV curves that are acquired in a typical degradation study, and you can move your mouse on top, and you can see its point. It's very interactive. While on the right, we have a summarize, which again, you can fully customize it. For example, we can choose to plot the power conversion efficiency in the y-axis, as I do now, and the time in the x-axis. You can see you have a typical degradation curve. You can change the color depending, for example, on the temperature, and the size of your points depending on the fill factor, for example. And this is really easy to generate. So you can see that you have the fill factor is changing with time as well with the PC. While, for example, if we plot, you can see that if you scroll, it's very interactive. If you show the size in function, for example, of the open circuit voltage, this is much more constant compared to the fill factor. If you use the short circuit current, this varies still a lot. So this is just an example of what you can do with database, this kind of tool. And it's really easy to generate it. So the benefits of this system is that it's compact, it's an all-in-one measurement tool, it has database integration, and it is low cost. And more importantly, all the round robin's partners can use the same equipment to test their device, and also to make sure that we know, and every partners know the condition inside the aging chamber or the environment where they are measuring. So therefore, we would like to introduce the Suitcase 2.0 round robin and encourage you to pre-register at the website for photovoltaic.org/MMkit. Yeah, you can insert your information and you will receive updates. And I want to point out that you're not just signing it for receiving the MMkit to test your device in a round robin, but you're also entering something that I like to call a global virtual lab. And the way we think about it is that each of you will be able to measure, and you can automatically transmit your data in the database, and also you will have access and you can plot not only your own data, but also you will be able to plot and compare your data with the other partners of the round robin. So you will have a very fast and very quick way to directly compare if what you're doing is as a good match among the partners, and this is very powerful and very easy to use as well. So concluding, I think I've shown you that we need more control in order to achieve a better reproducibility, and we provide a new tool to do that. We also believe that software approach for data comparison and analysis can improve the understanding and the intercomparison of device structure and lifetime. I would like to acknowledge some of my colleagues, Enric Dam, Rafael Valverde, Suren Gaboyan, and Martin Malsen for their help. And thank you all for your kind attention.
Okay, thank you for the interesting talk. Are there questions?
For measuring the current, you went a little bit quick there. The thing you use to measure the current, is this commercially available? Because you put their DTU source meter.
Yeah, that's not available.
Okay, because you put a price, I think, but...
Well, yeah, it's a estimation of the price that it costs to us. So we ordered its tool that we need to develop the circuit, and that's what it costs to us. You cannot buy it. This is not inside. This is something that we provide for our partners for free. Yeah.
You can measure IV curve.
Yeah, you have if I recall you the demo I show, all the data that was shown there, so also the IV curve in the left bar. I'm sorry I went a bit fast probably, but that was all acquired with this tool. So you can measure IV curve, you can...
Then you load it into the web page in the same database, and you can compare all this.
Yeah. Yeah, we will give you more details about this, of course, but it's already working, and I think it will be a powerful tool for the next round robin.
Are you going to be here the next 2 days?
What?
Are you going to be here the next 2 days?
Yeah.
No. Yeah, no.
Okay. Are there more questions? Oh, one in the back.
I didn't understand if in this round robin your idea is to send only this box, this tool, but also the device to test, or only the tool for testing?
Okay, so we haven't gone in detail yet with the next round robin, but the idea, I call it like the Suitcase 2.0, recalling to the Suitcase round robin that I show in my overview of the previous round robin. So the idea is that you will have a suitcase with some device, and also the MMkit. So we will replace the multimeter with a fully tool to measure everything that you need to fully characterize your device, and also the software that is talking to it. So you will be able to analyze the data, to compare with the other partners in almost real time.
Because I am a little bit afraid that if you share devices and setups to measure the devices, then at the end the round robin doesn't really make too much sense, because obviously all the results will be very well comparable, but there is not much sense, in my personal opinion, to...
I can agree.
Okay.
That you.
That's my personal one.
I think it's a very good idea because you can send that with all the partners and do the IV curves, all the partners at the same time, the same equipment, the same specific IV curves measurements, etc. And you compare what your IV curves also. So you can have both and compare. It will be very good to see difference with the laboratory setup and difference with the same equipment. It's like a reference solar cell, for example, reference equipment. I think it's a good idea.
If all of us measured by the same equipment, maybe it's a good idea to do, I don't know, you call it round robin or not, to measure it outdoor at different locations. And in this way, we will really see effect of atmosphere, temperature, light spectrum, intensity, whatever. This can be very accurate. Maybe it's not round robin, but it can be good. Good inter-laboratory study.
I think the possibilities are a lot. We have to decide.
Soren, did you have a question? A comment.
Thanks. Actually, thanks, Giorgio. It is quite an important point that you raise. So, in principle, what is Michael showing here is sort of a concept. So, meaning, eventually, I mean, everyone is welcome to, why not, try their own devices as well with the same equipment. Now, the concept itself is that what we're trying maybe to do with this, first of all, as was suggested, we're, for example, testing light sources, we're testing different geography locations, but then also the main point here is what Michael calls virtual lab, meaning that we are sort of creating this worldwide database where people can upload results of both their devices or someone else's devices and compare. So some sort of ideology of bringing, let's say, the world together. So sure, I think maybe we start with one type or a few types of devices, and maybe that goes further to even more types eventually. Yeah.
Okay, more questions? If not, let's thank Michael again for the nice presentation.
Thank you.